Here is an example of how we can calculate the electric field created by a point charge using Gauss's law. We'll start with the point charge, with the charge plus q, and we will ask what is the electric field created by the presence of that positive charge at the distance r from it. We'll surround that point charge by a sphere, that will be our Gaussian sphere, and we'll explore here a little bit the symmetry of the problem. We have spherical symmetry. What this means is that the electric field vector has to point outward or inward, but it has to go along the radial direction. In this case, we know it's going to be outward because of the charge being positive. Not only that, but the electric field vector will have the same magnitude as we move along the sphere. Gauss's law says that electric flux through that sphere, which we calculate as EEdA cosine theta, has to be equal to the charge that we have enclosed with the Gaussian sphere divided by the epsilon naught, here the epsilon naught being the permittivity of free space. The left-hand side, the electric flux, is the product of the electric field vector and the area vector, and the cosine of the angle between the two. For the Gaussian sphere, we have the area vector pointing outward again. Remember, dA here stands for the area vector having magnitude equal to the area of that small surface that we're considering in direction outward. The angle in this case between the area vector and the electric field will be 0, so we'll have cosine of theta equal to 1, and so the integral is actually simplified to E dA. Again, remembering that the electric field remains constant in magnitude along the surface of the sphere, we can take that constant outside the integral, and the integral over dA is simply the area of the sphere, which we know from mathematics to be equal to 4 pi r squared, and here r is the radius of the Gaussian sphere. And so we get for the result that the electric field created by a point charge with a charge q is equal to 1 over 4 pi epsilon naught q, the enclosed charge, over r squared. Compare that with the Coulomb's law. We know that the force between two charges is equal to 1 over 4 pi epsilon naught q1 q2 over r squared. In our situation, if q1 is simply the charge at the center plus q, and q2 is that test charge plus 1 coulomb that we use to test for the electric field, the Coulomb's law will give us the force equal to 1 over 4 pi epsilon naught q over r squared. And so using the definition of electric field being the force per unit charge, we can actually divide by that plus 1 coulomb test charge, and we arrive with the same expression for the electric field.